Hello and welcome once again. This week's video is going to be on trigonometry and Pythagoras. So we're going to be looking at a few questions today, probably about sort of half an hour or so, maybe a bit longer to look through these. Again, all of these questions very similar to exam questions that have gone in the past on trigonometry and Pythagoras. We're going to do more difficult trigonometry at some stage, probably a little bit later this evening, but I'll put that up on YouTube as soon as it's available to you. Just once again a reminder that if you're watching this on YouTube, I'd really appreciate it if you can click the like button and subscribe, and if you want to suggest topics for me to do in future chats and podcasts, please do so by putting that on the chat, which you'll find on the Twitch panel, which is next to the Twitchcast on the screen there. As usual, this is small bite-sized chunks for GCSE mathematics, revision topics only. If you want to see topics from scratch, you can do so on lots and lots of other videos on YouTube. This is really predominantly concentrating on exam type questions. So if you're working towards your GCSE mathematics for the summer, this we're helping you a little bit for that. So off we go then, looking at a few questions on trigonometry. You can see this question right here. This is becoming a bit of a favourite. Doesn't occur all the time, but certainly is coming a bit more common, asking you about the area of a triangle and proving that the area of a triangle is given by half AB sine C. Now, often you're asked about the areas of a triangle with this particular formula with non-right-angled triangles, and you can see that this is not right-angled. You have to sort of construct an idea about how you're going to create this formula, this particular formula, and this proof should hopefully have been shown to you by your maths teacher when they taught you half AB sine C. But if you don't know it and you're not sure, you haven't remembered it, the best thing to do is to start off by thinking about what the area of a triangle is. Now we know that the area of a triangle is half the base times the height. That's half of this distance here times the perpendicular height from the bottom to the top. So it would be really good to draw that. So I'm going to draw that firstly on my shape to show you where that line goes, just to demonstrate where your height is. So this height here, 90 degrees to the base, and you can see this would be the height representing all the way from the top to the bottom. Now, this length here, A, is the whole thing, all the way from B to C. So this one here we don't yet know, but it doesn't matter necessarily because, again, the area of a triangle is still half of this base times the height. So half of A times whatever this height is. Now this has formed a right angle triangle. I've drawn the 90 degrees in the corner, and you do know something about this angle in this corner here and that side and this length here, and that is that this length and that length and this corner and this angle here do have a relationship. We all know what those relationships are, and again, just a PowerPoint to show you some of the basic relationships that you should remember. These are the three relationships which you've hopefully remembered by now, the sine, cos and tan relationships. Sine theta is opposite over hypotenuse, and you can see the right angle triangle there with the opposite and the hypotenuse drawn in. Cosine theta is adjacent over hypotenuse, and then again tan theta opposite over hypotenuse. There are several ways of remembering that. I tend to teach my students to remember a rhyme. This is one rhyme, or you can remember the phrase Sokotoa, that's the old favourite. Several ways to remember it. But just make sure you've got that down because you will need that on exam day. No longer do you get given that on a formula sheet. It's this relationship that we need, however, the top one, sine theta, because that one is relevant here. Because here in my right angle triangle, looking at this height here, this height and this hypotenuse are related. If I give this a name, I'm trying not to call it height because that might confuse you with regards to hypotenuse. So let's just call that x. Okay, with a circle around it. This is the opposite because it's opposite this angle here. This angle here, that's opposite there. And this is the hypotenuse, the longest side of my right angle triangle that I've just traced out for you. So we do know that sine of this angle, sine of big C, this angle in the corner, is opposite, so that's the x over b. So x over b is sine C. So little x over b is sine C. We want to find out what this height, this x, is. So hopefully you can see that you would just be multiplying this sine C, the length here, just move it slightly, this sine C, this length b by sine C here. So that's the length here, the height. You could write here b sine c. That's what this is, b sine c, all the way from the top to the bottom. Earlier on we decided, we knew that the area of a triangle is half of the base times the height. So half of that a times this height. So it's half of the base a times b sine c, which is the same thing as this formula they're trying to get you to show, which is half ab sine c, and that's the formula they're trying to get you to show. So you just write as proved there to show that you've proved it's the same relationship. It's very straightforward, not hard to show, but just something to remember for exam questions. This second one here, question 2 we'll look at here, is a much harder question. This is much harder, but still ways in which you can remember what's going on here. There are, again, some things that I'd like to draw your attention to. So most predominantly, just remembering, please, the relationships. And again, your teacher should have concentrated on this for you, but you do need to know these 3 relationships. So sine theta, you must know that's a half, please. Cos theta, you should learn that that's root 3 over 2. So root 3 over 2. And then tan 30, finally, that is root 3 over 3. So root 3 over 3. All of these things are related, and you just do need to have that in your mind, what these things are. So sine 30 again is a half, cos 30 is root 3 over 2, and then tan 30 is root 3 over 3. Those relationships you do need. Now this particular question came up in a non-calculator exam, so this is something you're going to need to remember off the top of your head, and this relationship you're going to find here is very complex. It's quite a difficult question to do if you don't remember your facts from earlier. So those facts from earlier, very important for you to have in your mind, because you'll definitely need them for this particular question. Now, this says here, the diagram shows 3 right-angled triangles. So we're in right-angled trigonometry mode. It says prove that y equals 3/4 of n. Well, first of all, we've got some clues. So if we look at this big triangle, first of all, this big triangle has got 30 in the corner. N here is the opposite side, and it would be quite useful to work out this, because if the strategy should be that if we can work out this, we can then work out that, because we can use a trigonometric relationship between these, and if we can work out that, we can then write an expression for y. So the strategy is work out this, work out that, use an expression to work out y, so we can get this expression working. So that's the strategy. You've got to sort of formulate that to start with, because if you don't have that in your brain, you really are going to struggle with this particular question. And this happened to be, although it's my question too, this happened to be the last question on the paper, so it's meant to be the hardest question on the paper. So it is very difficult to do. So first of all, let's look at this length here. This length here is, in terms of this angle, it's the adjacent side, because this is the adjacent, that's the opposite here, over here. That hypotenuse we don't really need, it's not relevant here, but this is the adjacent side, that's the opposite. So we need a relationship that's relating that and the adjacent with the angle, and that has to be tan, because that's the only relationship that relates those things. So we know that tan 30 equals the opposite over adjacent, that's n over a, so I'm going to write little a in there to show that that's the a. So my adjacent side is underneath in this example, so I want to try and work out what tan 30 is. Well, I've learned tan 30. Tan 30 was in that chart I showed you earlier. That's root 3 over 3. So we've got the relationship as root 3 over 3 equals n over a. I want my a. I want to find out what that is. So I have to maneuver this around to make a the subject to the formula. So hopefully you can see how you would do that. You're just going to be doing a little bit of division, root 3 over 3 underneath. And again, if you divide by a fraction, it's the same as multiplying by the fraction upside down. So if you maneuver that, sorry to be squeezing this in, but you'll hopefully see this. That's what you get. So a equals 3n over root 3. Now 3 over root 3 is just root 3. So this is just going to be a equals root 3n. So that's my expression for a, root 3n, which I'm going to write in now. Now when you get to that, just going to cross it out there. When you get to that, we've got then really to look at this second triangle, and this second triangle has got this is the hypotenuse now in my second triangle, and again the strategy was to try and work out this one. And again, this is the adjacent length, that's the hypotenuse, this is the angle 30, so I'm looking at a cosine relationship, adjacent over hypotenuse, and then this cosine 30. So again, I'm going to try and squeeze this in probably underneath here somewhere. So cosine 30 equals adjacent, which is this length here. So let's just call that, I don't know, b, I suppose. And that's over root 3n, which is my expression for this distance. So b over root 3n. Again, I'd like the b, I'd like to know what b was. So I'm going to write cos 30 and then root 3n cos 30 is b. So root 3n cos 30 is b. It's just multiplying that by that. Now cos 30 we learned earlier, and we learned what that was, and cos 30 is root 3 over 2. So I've got root 3n times root 3 over 2, because we learned that cos 30 was root 3 over 2, and that's b. These two root 3's multiply together to make, well, just 3, because we've got root 3 times root 3, that makes 3. And then it's got this 2 underneath, so 3 over 2n is the expression I'm going to get. It's becoming more straightforward as I go through. So 3 over 2n is this side up here. I'm just going to point to it for you. So this is 3 over 2n, so I can now write that 3 over 2n. Lastly, I just need to bring it down slightly. This last triangle, we've got 30 in the corner. This is now the opposite side, the y, and this is the hypotenuse. So I've used tan in that one, cos in that one, and this one I'm using the opposite and the hypotenuse. That's the sine relationship. So it went tan, cos, sine, and we're needing to write down the expression with sine 30 in it. So again, this is a good question because it tests all three relationships and all three ratios. So I'm just going to squeeze this to the side here so you can see me working on this. So sine 30 in that last triangle is opposite over hypotenuse. The opposite, just going to show that real quick, the opposite was y. So I'm going to show that again. So y was the opposite here. So opposite over the hypotenuse, which here was 3 over 2n. It's quite complicated, and that's what I'm writing down there. And then I need to get an expression for y here. I've got to prove that y is 3/4 n. So let's just multiply this up first of all. So I've got 3 over 2n times sine 30 equals y. So 3 over 2n sine 30 equals y. And we learned earlier that sine 30 was, well, a half. So that will be 3 over 2n times a half. That's equal to y. And 3 over 2n times a half is 3/4 n. So this is the final proof. 3/4 n is y, and that, let's put it to one side here, that is what they were trying to get you to prove earlier. So it's the same thing, just written back to front, it's the same thing, you can hopefully see that, and that's what you would need to do to get that proof through. It's quite an interesting question because you've got all the three relationships being used, all three ratios being used, all this learning that you had to do, sine 30, cos 30, tan 30. If you don't know those things, you really are in trouble for this question. This was the last question on the non-calculator paper, as I have just mentioned, so it definitely was meant to be stretching. But if you know your stuff, that's quite an easy question to get marks through, and it's well worth just figuring your way through. This question here, again, very commonly sort of asked sort of question. Quite an interesting question again for a variety of reasons. This one's showing a triangle inside a rectangle. For this question, it's quite interesting. You don't need to use anything other than Pythagoras and what the area of a triangle is, half the base times the height. That's all you need for this particular question. There's nothing else you need for this particular question. So it's very straightforward, actually. It does ask you again to show something, so it's asking you to show there, I hope you can see that, the triangle, the area of triangle, this triangle in here is 8. Okay, so just be aware that's what it's asking you to show. And again, very straightforward, the philosophy and strategy that you need to use to do that. So the first thing you've got to do is work out the area of the rectangle. This is the strategy. And then you're going to take away the area of this triangle, the area of that triangle, and the area of that triangle. And that's what's going to give us this thing in the middle. Okay, many candidates this particular year did a common error. And the common error they went for was to work out this length here, and then do half the base times this height with using Pythagoras. But you can't assume that any length you put in there, any ruler line that you draw in there, is exactly halfway down that particular length. You can't assume that. So you have to be very careful about any assumptions you make. So the only thing we can assume is that these are all right angled triangles, which you can see they are, and also that we can work out these lengths of these sides on this rectangle by using Pythagoras' theorem. That's the only thing you can do. It's important to mention that it has said the diagram is not accurately drawn for a number of reasons. You shouldn't just go assuming certain things about it. So it's important just to go ahead and have your strategy in your mind. So if you ever see a question like this, strategy's always got to be work out the area of the big thing, work out the area of the little things inside to work out what's left, and go for that strategy all the way through. So we're going to work out the side length, this CD length first of all. We're going to work out what that CD is. And again, hopefully you can see this right angle triangle, CDF. That's this right angle triangle in the corner here. I'm going to put the right angle sign there so you can see that in there. And we're going to use Pythagoras' theorem. This is the hypotenuse in my right angle triangle to work out what this is here. So this is, Pythagoras says it's this squared minus that squared, and that's what this is going to be. So I'm going to call this a length. Let's call that A again, just because it's just the first letter that's occurred to me. So we're going to use Pythagoras' theorem here. I'll do it to the side. So Pythagoras' theorem says A squared plus 2 squared equals 2 root 10 all squared. Okay, important. I'm using brackets just to show you the distinction there between all these things. Now, this 2 root 10 is the same thing as root 40. So if you took the 2 inside the brackets, you'd have a 4 in there, and that's root 40. So this is root 40 in there, and of course you're going to be squaring that in a minute. So, and this here, 2 squared obviously is there. So root 40 squared is obviously 40. This 2 squared is 4. And then you've got this A squared here that you left to the side. So we want to work out what A squared is. Hopefully you can see you just take the 4 away. So you get 36. So didn't have to reach for a calculator just yet. And A is 6. We always assume the positive root on these questions because they're distances. So A is 6 centimetres here. So we know that A is 6 centimetres. So the area of my rectangle is 6 times 4, 24. So my total area, 24. First of all, let's write that down. So total area, just going to show to the examiner what I'm showing them. So again, 24 centimetres squared for the total area of the rectangle. So I'm writing that very clearly to the examiner to indicate I know what the big rectangle is. You're probably going to get some credit for that for sure. Now next to the strategy we're going to do is work out the area of all these individual triangles. So we're going to work out this triangle here, this triangle here, this triangle here. You can see I've called them all number 1, number 2, number 3. So number 1, first of all, area of triangle number 1. Okay, half the base times the height. So half of this 2 times this height, which was 6 from earlier. So half of 2 times 6 is, 2 6s are 12, and half of that is 6. So it's 6 centimetres squared. You can do that in your head. Very easy. This area 2 here, again, if this is 4, because this has to be the same as that one. And this whole thing was 6, so this length here is 4 between there and there. Okay, so I just showed that for you. So this is going to be 4, that's 2, this is 4. So the area of this triangle here, number 2, is going to be half the base, so half of 4 times 4, so 2 times 4, 8. So we're going to write that in. And then the area, finally, of number 3, again, half the base times the height, so half of 2 is 1, and then 1 times 2 is just 2. Okay, so those are the 3 areas we've got. So area 1, area 2, area 3. Very straightforward so far. So we're going to add all those 3 things up. So 8 plus 6 is 14. 14 plus 2 is 16. So the triangles is 16. All the triangles add up to 16. Okay, so the area of triangle is 16. And that must mean that the area of this triangle left, so it's DEF, this DEF in here, this area has got to be 24, take away the 16, that has to be 8. So the area DEF is 8, and that's what they were asking you to show. So you just write a little 2 lines to say, I've shown that that was 8 centimetres. Really straightforward, not massivly difficult, only needed to use the area of a triangle. The hardest bit was just doing all this stuff over here with the Pythagoras theorem. As long as you can do that, you're fine. This question here, again, they're becoming a little bit more common now. They're not asking you basic SOHCAHTOA problems. They're asking you problems that require you to know that sine, cos and tan are simply ratios in a shape. And that if they're ratios in a shape, they are preserved according to the size, because all these triangles are similar triangles. And again, it requires just a little bit of understanding, just to understand what's going on. So this particular question is saying, here is a triangle PQR, so PQR. The length of QR is 60% of the length of PR, so 60%. Find the value of sine QPR. So the first thing I'm going to do is label that angle in here, okay, just so I've got that understanding where that angle is. That's the angle QPR. I want to know that this is QR here, it's QR's length here. It's 60% of the length of PR, 60%. So this is 60%, and that's 100%, because it's this 60%, that's 100%. Then the relationship between them is always preserved. So if this is 60 for that 100, so this is 60 for that 100, I can write that in. So if that's 60, that's 100, so that's just converting the percentages to some sort of mystery length. The relationship is going to be always preserved. So if we're looking at sine, and the relationship sine, we're thinking through, okay, we need to figure out how this relationship works. So this relationship, because it's similar triangles you're talking, this relationship's always preserved. So we can divide these numbers down to make it easier for ourselves. So if you think about what 60 to 100 is, okay, 60 to 100 here, we can write that in very, very simple form. So in its simplest form, this relationship is going to be 6 to 10, and then again 3 to 5. So you can break this down real quick into a very simple relationship. So we can think of this as 3 and this as 5. Okay, just breaking these down into simpler numbers. I don't really want to work with 60 and 100, so I'm going to break it down in simple numbers. This is okay because you're only looking at the sine relationship, you're looking at the relationship, not any particular lengths or anything like that. So just asking you for a sine relationship. So you just have to have an understanding that it's okay. The relationship's preserved across a triangle that's of different lengths as long as it's similar to the one that you started with. So this is 3, this is 5. Now, Pythagoras' theorem says that this length here, the hypotenuse, is that squared plus that squared. 5 squared, 25, and that squared is 9, and then obviously the square root of those things. So this is going to be the square root of 5 squared plus 3 squared, and 25 plus 9 is 34. So this is the square root of 34. So this length here is going to be the square root of 34. Now here's where the question gets clever, and there was a lot of candidates that would have made this mistake. You're not asked for the actual angle. You're only asked for the sine QPR. Sine QPR. And we learned earlier that sine QPR is the opposite over the hypotenuse. That's this length here, which we've called 3, over the hypotenuse, which is root 34. So 3 over root 34. That's what sine QPR is. You're not having to work out the actual angle. It doesn't ask you for the angle. It asks you just for the sine relationship. So all you've got to do is take your calculator and work out what 3 over root 34 actually is. And again, modern calculators are pretty good at working out these things. So I'm just going to show you on the calculator real quick what I've typed in. So 3 divided by root 34. Apologise for the screen flicker there. So 3 over root 34, you get this horrible horrible fractional answer. But if you press SD, which I'm going to show you here, SD, I'll try and get that in focus for you, there you go, SD, that gives you 0.514. We stop at 0.514 because this question particularly asked for 3 significant figures. So 0.514, that is what sine QPR is. So it only asks for sine QPR, not the actual angle. Sine QPR, 0.514. That is the answer, and you stop there. If it had asked you for the angle, you'd have needed to have done an inverse sine of that, but it doesn't. It asks you for sine QPR. So that's the main thing I wanted to point out about this question, which is why I picked it, is that a lot of candidates went on to work out the angle and then obviously got it marked wrong because you weren't writing down sine QPR. So just be aware of that and be wise to that sort of tactic. This is the last question now on this selection. I just wanted to look at this one real quick. Again, very commonly sort of question. A lot of lengths put in here. This is 4.5. You can, if you can't quite see that, 7, and this is 15 centimeters here. And it's sort of a quadrilateral, so it's a 4-sided shape, but there's a right angle triangle inside. And it's asking you to work out the size of angle KLM. So again, I'm going to mark in where angle KLM is, just to demonstrate to the examiner, okay, I know that's the angle they're looking for. It's a right angle triangle. This is the hypotenuse of my right angle triangle. It would be really useful to work out what this length is here. So I'm going to call this length here, I'm going to call this little a again, just because just use the first letter of the alphabet. So I'm going to call that little a, this length from here to here. I'd be able to work out a strategy from this and this, because this is a right angle triangle also. So we can use Pythagoras' theorem to get this length, the hypotenuse of my first right angle triangle, and that's very easy to do. So we just do 7 squared plus 4.5 squared, and then square root that. So 7 squared plus 4.5 squared, and then square root it to get this length A. And again, you are allowed to use a calculator for this. So I'm going to use the calculator just to do that, and you can do that real quick. And you would get 7.826237921. Now it's good practice to write the whole thing down. Why is that? Because you're going to need this in a minute. What you shouldn't do is round it up too early, because we're going to need this length in a minute. So this length here is 7.826237921 centimetres. But we're not going to round up too early, because if we round up too early you might get carried away from later on. So we want to make sure that we leave this as vague as we can, as accurate as we can, and round up only at the end. So I'm only going to round up right at the end. Now that I know what this is, I'm looking at this right angle triangle and I'm working out what my angle is going to be. And my relationship here, well, we're looking at the opposite side, so this is opposite to there, this is the hypotenuse, so sine, opposite, hypotenuse, this is the relationship that I need. So it's very straightforward that sine of my angle KLM equals the opposite, which is my little a, over the hypotenuse 15. So that's what I want. My A is down here, so 7.826237921. Going to put that in there, and we're going to work out what that is. So just give myself some space, and I'm going to write out what sine KLM is. So what I'm doing is I'm putting into the calculator now, I'm putting in 7.826237921 divided by 15. That's all I'm going to do. So I'm going to put that into the calculator, and I get this, which I'll just show you. I get 0.5217491947. So very long number. Again, writing down the whole thing, because when I come back and check, it will be really handy to be able to check these sorts of things. So if I write down these things, I can come back and check to make sure I haven't mistyped a button or anything like that. Now, unlike the previous question, this one is asking for the angle, so I'm going to be doing an inverse sine now. Inverse sine of this horrible 0.5217. It's important to get your presentation right, so do learn how to write these out in brackets. I've seen lots of mistakes, people writing these wrongly or people writing the format wrongly. You're going to do inverse sine of all this stuff here. So again, your calculator can do that all in one step, and at this stage your calculator is good enough that it will be able to do that all in one stage. And we're going to get to, again, 3 significant figures. I'm just going to point that up there. So 3 significant figures is 31.4 degrees. So 3 significant figures, only rounding up right at the end. The actual answer was this, 31.44965733. But we're going to round it up to 31.4, so only 3 significant figures here. Okay, that's all the questions I had on trigonometry and basic Pythagoras. I hope that was useful. Do keep working hard. I wish you all the best for the summer. Good luck, and see you soon. Bye-bye.